All right, today we're going to tackle one of the most important ideas in all of trigonometry, the phase shift. We are going to break down what it is, exactly how to find it, and, I think this is the coolest part, why it's not just a math problem, but something you can see all around you.
But before we dive in, here's a little puzzle for you. What on earth does a delayed echo have in common with the summer solstice, the longest day of the year? I know, it sounds totally random, but just hang on because the answer is actually the key to understanding this whole concept.
So let's start at square one. Before we get into all the numbers and graphs, we need to get a really solid handle on a basic question. What is a phase shift anyway?
At its heart, a phase shift is just a horizontal slide. That's it. Imagine you have a beautiful wave, like a sine curve, and you just grab the whole thing and scoot it to the left or to the right along that x-axis. What's crucial here is what isn't changing. Its height, or amplitude, stays the same. Its width, the period, doesn't change either. The only thing you're messing with is its starting line.
You know, a great way to picture this is to think about an echo. The echo is the exact same sound, the same pattern as your original shout, it's just shifted in time. It gets to you a little later. Or think about electrical signals that have to be perfectly timed. You're just shifting them so they line up. In every case, the wave is identical, it just begins at a different point in time or space.
Okay, so that's the what. But how do you actually spot one in an equation and know which way it's going? Well, this leads us to the core rule. And fair warning, this is the part that feels a little backwards at first.
And here's where your brain might do a little flip-flop. When you see an equation like y equals sine of x minus c, that minus sign, it actually means you shift the wave to the right. And you guessed it, when you see y equals sine of x plus c, with that plus sign, you're going to shift it to the left. It's the complete opposite of what you might naturally think.
This is the one thing you absolutely have to burn into your brain. If you walk away with just one nugget of information, let it be this. Subtract means right, add means left. A simple way I like to think about it is that subtracting means a delay. Things happen later. And on a graph, later is to the right.
Okay, so you've got the basics. You're feeling good. Now let's throw a little curveball in there, because this next part is, without a doubt, where most people get tangled up. It's what happens when there's a number, which we call b, right next to the x inside those parentheses. On the screen, you can see the classic trap right next to the correct way to handle it. You see an equation like sine of bx minus phi, and it is so tempting to just say, oh, the shift is phi. That is the trap. You absolutely must factor that b value out first. When you pull it out, the equation becomes sine of b times x minus phi over b, and that right there reveals the real phase shift is actually phi divided by b. Honestly, getting this step right is the secret to solving these problems.
All right, enough theory. Let's get our hands dirty and actually graph one of these things. We'll put all these rules together and walk through it step by step.
Okay, let's work through this example. Y equals sine x minus pi over 4. Step 1, where does our cycle begin? Well, that x minus pi over 4 tells us everything. It's a shift of pi over 4 to the right. So our new starting line is at x equals pi over 4. Step 2, we need to find our other key points. All we do is keep adding the quarter period, which is pi over 2 for a basic sine wave, to that new starting point. And finally, step 3, we just apply that classic sine wave rhythm, 0, then max, then 0, then min, then back to 0, to our new shifted x values. And there you have it. It's the same exact sine wave, just slid over a bit.
Look, knowing how to do something is half the battle. The other half is knowing what not to do. So let's talk about the two biggest, most common traps people fall into with phase shifts so you can sidestep them completely.
First up, the classic mix-up, getting the direction wrong. It is just so natural to see a minus sign and think left. You've got to train your brain to fight that impulse. Just keep saying it to yourself like a mantra. Subtract equals later, which means right.
And here it is again, the other big one we talked about, forgetting to factor out that b value. You look at sine of 2x minus pi, and it's practically screaming at you that the shift is pi. But no, you have to factor out that too. And when you do, you get sine of 2 times x minus pi over 2, and bam, the real shift, pi over 2, reveals itself.
So after all this, you might be thinking, okay, I get the math, but who cares? Well, this is where it all pays off. Let's circle all the way back to that question I asked at the very beginning and see how this works in the real world.
Check this out.
This equation might look a little intense, but it's actually describing something you experience every single day: the number of hours of sunlight. The amount of daylight throughout the year is a perfect wave, right? The days get longer and longer, hit a peak, and then get shorter again. But of course, the longest day of the year isn't New Year's Day.
And that's where our hero comes in. Look right there. You see that T-minus 80? That is the phase shift. That little piece of the puzzle shifts the entire daylight cycle about 80 days to the right. And what does that do? It perfectly aligns the model with reality, making sure the peak of the wave, the most daylight, lands right around day 80 of the spring, exactly where the summer solstice belongs. It's amazing.
So it turns out phase shifts aren't just some random thing in a math textbook. They are literally the tool we use to make our mathematical models line up with the real world, from the sound of an echo, to the electricity in our walls, to the changing of the seasons. Now that you know how to shift a wave, think about it. What other patterns and cycles out there could you now describe with math?